Hello, good morning. Okay, so everything should be okay. You should see my desktop and you should hear me. Does everything seem all right?
Yep, everything looks good.
Great. Okay, and I hear everything. Good. All right. So today we're going to start talking about virtual memory. Okay, so we're going to start talking about this section on what's the idea behind the abstraction of virtual memory, not yet the mechanism. See, the reading for Wednesday is the mechanism, how we're going to do create virtual memory, how we're going to create virtual memory. Right now, we're talking about the abstraction. What is it we're trying to do, and then how we're going to do it. And we're going to see several ways of doing it. Yeah, of the how is going to be there's several ways. We're going to start with the baby way and work our way up to the modern way, kind of like that we did with scheduling. Started with a baby way and worked our way up to the modern way. So we'll see several different mechanisms. Okay, but mechanism is the how. The abstraction is the what. So what is it we want to do, and then first what is it we want to do, and then how are we going to do it? Okay, so um, the abstraction is abstract and it's a little bit hard to explain. Um, we're going to give it a try. Sometime after we've gone through some of the mechanism, it's probably going to be a good idea to go back and talk about the abstraction because it might make a little bit more sense, kind of talking about what it is we're trying to do. Okay, now actually, one way to think about it before looking at what the book says is we're trying to go back to a picture we drew some time ago. We drew this picture when we were talking about the other abstraction, the abstraction of processes. Okay? And we said that this is an example of two processes running. There was process 0 and process 1 in memory. Okay, and we were talking about the virtualization of the CPU. That the CPU, by having having a kernel mode user mode bit, when the CPU was in user mode, it's like a virtual CPU. So the CPU in user mode creates like a virtual CPU that's more restricted in what it can do, and it's restricted to this memory range, and that's running this process. And the virtual CPU, now, and this is what part we didn't say anything about. How is it that this CPU over here, when it becomes this virtual CPU, can't see outside of that red box? Yeah, yeah. And then when the timer interrupt comes and you switch back to kernel mode, in kernel mode, you can see everything in memory. But yeah, we want to talk about how that works. But when the CPU is in kernel mode, it's a physical CPU, not a virtual CPU. It can see all of memory, and it does something to switch to this other process. And then it goes back to user mode, becomes a virtual CPU, and it only sees this memory down here now. So how does the CPU only see this memory when it's running this process, but the CPU only sees this memory when it's running this other process? Okay, that's what we want to get at. Now, this red box here of memory is what we can think of as virtual memory. And that's the abstraction that we're trying to build, this abstraction of virtual memory. And we'll be more precise because right now it's not very virtual. It's just this range of memories. So right now, the way the picture looks, it's that the CPU only sees this range of memories when it's running this process, and it sees this other range of memories when it sees this other process. But that, if that was the way it worked, that the CPU was restricted to a range of memories when it ran this process and restricted to a range of memories when it ran this process, that would be not a very useful abstraction. And we'll explain why. It turns out that something more sophisticated is going on. Okay, so the what we're trying to create, it's a little bit. Here's another picture. Okay, I drew this by hand instead of using a drawing program. Okay, it's a real similar picture. It's got a little bit more. It's in some ways it's got more detail, in some ways it has less detail. I mean, here's the CPU. The CPU is a program counter and instruction register and a bunch of other registers. Program counter, instruction registers, and a bunch of other registers. There's a mode bit. There's a timer that can interrupt the CPU. We're really going to be talking about this memory management unit. So there's this memory management unit here. Okay, and what's the detail, okay, in this picture, I show two processes over here. In this one, I just say all the processes are in memory somewhere. This is a little bit more general in that sense. Now, here is where things really are different in this picture. There is a certain number of uh, CPUs hold registers. Okay, these are registers. So there's a certain number of bits in that register. Okay, so right now those two registers are 64 bits. A few years ago they were 32 bits. A long time ago they were 16 bits. This thing only had had 16 bits in the register. Like right now they hold 64 bits. Okay, when you address memory, over here, memory is only 8 bits wide. Okay, remember we said that a long time ago that this is bytes of memory over here. These are bytes of memory over here. Okay, and there's a certain number of bytes of physical memory. Okay, the program counter holds an address. If the program counter is 64 bits, it's holding an address between 0 and 2 to the 64. You can't have 2 to the 64 addresses over here. That's a gargantuan number. Memory doesn't exist that's that big. For example, nowadays, most people have about 8 gigabytes of memory. 8 gigabytes of memory is actually represented by 34 bits. Okay, 34 bits is 8 gigabytes of memory, but the CPU has got 64 bits. Something's got to shift program counter addresses down from 64 bits to something manageable like 36 bits, which would be 8 gigabytes of memory, or 34 bits, which is 8 gigabytes of memory. Okay, that's what the memory management unit does. If you see, it's got I've drawn these arrows. The way you read this is that a virtual address goes into the memory management unit and a physical address comes out. We did that by just a single arrow here, whereas an address went in here and came out here. And here the implication was the memory management unit kept the address within this range when you're running this process. And the memory management unit kept the address within this range when you're running this process. And that's kind of what it is, but what we're going to do is the memory management unit is going to do an address translation. It's going to be, on the one hand, this thing made it too simple. Okay, it gets across the right idea that one process is in this chunk of memory, another process is in this chunk of memory. When the CPU is running this process, something should keep it from seeing these addresses. And when the CPU is running this process, something should keep it from seeing these addresses. So you can think of the memory management unit as this thing that kind of filters the addresses. When you're in user mode and you're running this process, somehow the memory management unit knew to filter out any address that wasn't in that range. And if you tried to give it an address that wasn't in that range, it would crash the program. Your program would get halted because it violated its restrictions. So this was thought of as sort of like a filter, a guard that says, oh, if the address is over here or down here, I block it, okay, and halt the program. If the address is within this range, that's fine, okay? And we'll see that that's kind of what the memory management unit does, but in fact, the memory management unit really does something a little bit more general, and that's actually the name of the next chapter. See, the name of the next chapter is address translation. So we're kind of getting at what we're really going to do. What the memory management unit takes in one kind of address. This thing here means the width of the address. So in the case of this is a 64-bit computer, this will be 64 bits. So in engineering, when you want to describe a bus that holds bits, you put a slash through it and the number n says how wide the bus is. So this would be, say, an n-bit address. Okay, like the timer is a 1-bit address. It only sends 1 bit up there. It says it signals 1 bit to say I'm interrupting you. Okay, So this would be N. In most in a 64-bit computer, this would be 64. In a 32-bit CPU, this one would be 32, because the program counter would be 64 bits, and the program counter puts addresses that would be 64. The memory management is going to do a translation down to the range of physical addresses. Okay, the physical if you have 8 gigabytes of memory, this range is from is only got 2 to the 32 possible 2 to the 34 possible addresses down here. So this would be 34 for M. So this thing would be translating 64-bit addresses to 34-bit addresses. That's going to be kind of the mechanism that we're going to use. Now, what that does is when the CPU is in user mode, the CPU doesn't know about the memory management. The memory management is controlled by the kernel in kernel mode. When the CPU is in user mode, the CPU doesn't even know the memory management is there. So the CPU thinks it's talking to a virtual memory address space. Okay, the CPU thinks I can issue any address between 0 and 2 to the 64. The CPU just does not know that there's any kind of restriction going on over here. The CPU, the virtual CPU, the CPU that would be this CPU here, the virtual CPU, it really thinks, unlike this picture where it thinks, oh, it's restricted from here to here, it actually thinks it has access to all of memory from address 0 all the way up to address 2 to the 64. Okay? Okay. So, let's see, picture doesn't quite fit because of the, okay. Oh. I can't really make the picture quite fit.
Professor, I just had a question.
Yeah.
Are we going to have another programming assignment?
Yeah, there should be one more. I think it'll be up there by Wednesday. It's not as hard as the current one, but it's about virtual memory.
Okay, thank you.
It'll be due at the very end of the semester.
Okay.
Yeah, so there will be one more about virtual memory, and I'm pretty sure I'll have it up there on Wednesday, and then it'll be due at the very end of the semester. Let's see, we're getting close to the end of the semester. We'll see. Right now, we are this week. We have 1, 2, 3 weeks of classes left after this week, right? If I remember right, and final exam is the second week of May. Is that right?
Exam week is the first week of May.
Oh, it's the first week of May, from the 2nd to the 8th.
Yeah.
Oh, then I was off by 1 week. Oh boy, I didn't look this up. So, yeah, so there'll be a homework. It'll be due at the end of this week. Yeah, just it'll be due, and it's nowhere near as hard an assignment as the current one you're working on. Okay, but yeah, there should be one more program assignment about virtual memory. So, yeah, I'll have to. There'll be a second exam, exam a little bit on virtual memory during final exam week, and I'll put some information about that up pretty soon too. Remember, let's see, go back to the syllabus. The second exam's during final exam week. So whatever the date, I didn't look up what date our class is assigned. It's the exam day.
I think it's on the Monday.
Probably the last several years, seems like all the exams are on Monday. I don't know if it seems like everything's either Monday or Tuesday. Okay, so it's probably on Monday. It was last year, it was on Monday. So that'll be the final exam will be that day. And then there'll be one more programming site. So there'll be one more exam on virtual memory and a programming assignment on virtual memory. Okay, so, all right, so in this picture, the CPU, when it's in user mode, is essentially the virtual CPU. It loses knowledge about the memory management unit. So it thinks it's actually talking to this virtual memory space that has all possible addresses. So see, if this is an n-bit address, the CPU thinks it's talking to 2 to the n memory locations. We call that virtual memory. That's the CPU thinking that it actually has the full address space available to it. And so it thinks there's one process sitting in there, okay? In fact, there is no virtual memory, there's physical memory, and this memory management unit is translating the addresses that the CPU spits out into addresses within a certain range, like over here, okay? So the addresses get spit out to within a certain range, but the CPU actually thinks it's talking to this entire range. For example, if this is 2 to the 64, and this is like on a most computers, something like 34 bits. So you've got, say, 8 gigabytes of memory over here, but this is 2 to the 64 is a truly tremendously large address space. There's no way that all these addresses can be working addresses. So what happens is if the CPU spits out an address that translates to something in that range, it goes through. But if the CPU issues an address that either translates to one of these ranges or translates to something that doesn't even exist in physical memory, because there's way more virtual memory than there is physical memory. So the CPU can issue an address that's not even within the realm of physical memory. And then again, the CPU just gets halted in that case. The CPU just doesn't know about the memory management unit. The CPU thinks it's access to all memory. And you can easily write your C programs to pretend that they have access to all memory. You can write a C, you can give your C program any address in hexadecimal and ask it to read that memory address. You just assign that address to a pointer and dereference the pointer. So you can actually dereference any one of these addresses. And your odds are very slim that if you pick that address at random, your odds are 0 that it'll be actually a valid address, because the amount of physical memory you have is just a tiny, tiny, tiny fraction of this address space, which is 2 to the 64. It's less than a billion. It's less than a trillionth. You know, it's the 2 to the 8 gigabytes is not even a trillionth of this physical address space. 2 to the 60. I actually made a table of these numbers before class. Here's what these numbers look like. 2 to the 64 is that number. And 2 to the 32, 4 gigabytes is this number. Okay. This is 16 million terabytes. And a terabyte is 1,000 megabytes. Yeah. Oh, no, I'm sorry, terabytes, 1,000 gigabytes. So you have 4 gigabytes of memory in your computer. Say you have 8 gigabytes of memory in your computer. That's 2 to the 34, 8 gigabytes of memory. This is 16 million of 1,000 gigabytes, which are, of 1,000 gigabytes. It's an unbelievably large number. Yeah. If you go from here to, after gigabytes, 1,000 gigabytes is a terabyte. That's 2 to the, I'm sorry, it's 2 to the 30 is a gigabyte. Oh, these numbers are really worth knowing, especially if you're going to work with hardware in any way. 2 to the 30th is a gigabyte. 2 to the 40th is a terabyte. 2 to the 50th is a petabyte. 2 to the 60th is an exabyte. Okay. What do these numbers mean? Right now, you buy memory in these units. 2 to the 30. So you buy like 4 gigabytes of memory. That's 2 to the 32. Or you buy 8 gigabytes of memory. That's 2 to the 34. So you buy memory in gigabytes. You buy hard drives right now in terabytes. Okay. A terabyte is 1,000 gigabytes. If you're a supercomputer, you buy memory in terabytes. They're now putting a few terabytes in memory in a supercomputer. Yeah, very few people have more than about 30. If you buy a really expensive laptop, you might put 30 gigabytes of memory into it. I don't know if anybody owns a laptop even with that much memory. I know some people, I know they sell them. I don't know anybody who has ever bought one, but if you work for a company and you're really doing high-end work, that company might buy you a laptop with 32 gigabytes of memory in it, okay? If you're working on a supercomputer, the supercomputer have several terabytes of memory, okay? But mostly we use terabytes to measure hard drives. A supercomputer now measures its hard drives in terabytes. Google measures its hard drives in terabytes, and they're starting to measure them in petabytes. Google, if it looks at all its storage, it's counting petabytes. Like if you ask how much storage space does YouTube need, it's in the petabyte range now. I think you can actually Google that. I forget how many, it's 320 petabytes. Yeah, so it's on the order of, it's in the hundreds of petabytes at this point, okay? And then the next range is going to be exabytes. And people are already starting to talk about designing computers where the storage space will be measured in exabytes. Right now, this storage space, no one computer. This would be all of Google's computers combined and all their data servers. They're measuring those in the petabyte range. Okay, but notice that 2 to the 64 memory is way more than that. Yeah, this address space, if you were actually literally to think of a computer that had 2 to the 64 virtual memory, it could hold all the data of Google, all the data of Google and Amazon combined. It could actually hold all the data of the whole world combined. This is a massive data space, that address space. It's really kind of crazy. This number 2 to the 64 is an unbelievably large number. Okay, so your 4 gigabyte memory space, which is this side over here, sitting inside of this virtual memory space is a tiny, tiny, tiny sliver of it. But the CPU thinks it has access to that much memory. Again, that much memory is more than the amount of memory in the whole planet Earth right now. Okay, Google measures its data in terms of petabytes. This thing was 16 million. Oh, actually, I should have translated. No, this is 16 million terabytes. In terms of petabytes, it would be 2 to the 14 petabytes. What's 2 to the 14? So it's okay. So it's 16 million petabytes. 16,384 petabytes. Okay. So yeah, if Google measures everything it owns in the hundreds of petabytes, and this is 16,000 petabytes, you can see that that's way more than all the data probably on the planet. Okay. So this is a massive address space. Okay. We'll probably never get computers that have anywhere close to that much memory. We'll probably never have computers that do hit that. Which is interesting because we went from 16-bit computers to 32-bit computers to now 64-bit computers. When we had 32-bit computers, they can only address 4 gigabytes of memory, but we hit 4 gigabytes of memory many years ago. When we jump from 32-bit computers to 64-bit computers, we'll probably never hit that much memory. Okay. People don't think there'll ever be a computer that has that much, where the computer would have the amount of physical memory would be the same as the amount of virtual memory. That happened with 32-bit computers. We ended up with physical memory way bigger than the virtual memory. With a 32-bit computer, the virtual memory is only 4 gigabytes, and we already have physical memory of way more than that. Okay, so in this picture, this number can be bigger or smaller than this picture, this number. The virtual address space can be smaller than the physical address space. That's the way it was for a few years ago when the virtual address space was 32 bits and the physical address space actually got to be around 4, 8, 16 gigabytes. You actually had the physical address space bigger than the virtual address space. But for most of computing history, it's been the other way around. The virtual address space has been bigger than the physical address space. This memory management unit actually works either direction. It can translate that virtual address up to a bigger address or translate it down to a smaller address. So the virtual address space can be bigger or smaller than the physical address space. Right now, we're interested in the case where the virtual address space is way bigger than the physical address space. Okay, so the CPU thinks when it's in user mode, when the CPU is in user mode, instead of thinking that it's restricted to that range of addresses or restricted to that range of addresses, which we kind of implied in this picture, we're switching point of view And we're going to say that when the CPU is in user mode, it has access to all addresses in the virtual address space. Picture's just a little too big. It has access to all the address in the virtual address space. Now, let's look at some pictures in the book to see how they explain this in a slightly different way using different pictures. Okay, so this picture is analogous to this picture here. It shows several processes in physical memory. See, I show two processes in physical memory. They show a process A, process B, and a process C. And there's some empty space here. There's some empty space here. Notice they put the operating system at the top. Okay, so they've got 1, 2, 3 processes in physical memory. And they wrote numbers like say, okay, this process has the range of address from 128 kilobytes to 192 kilobytes. The next one has the range from 192 kilobytes to 256 kilobytes. Then there's some free space. Then here's the range for that process. Okay, so the processes got to have a range to them. So this picture is he doesn't show the CPU, and he doesn't show the memory management unit, but he's showing memory, the same kind of idea that processes share memory. And this, I think he should have put the word physical memory in here. 3 processes sharing physical memory, because in the next picture, it's not going to be physical memory. The next picture is going to be more analogous to this picture, where he's going to show virtual memory. Okay. Now, what does one of these processes look like? Okay, his next picture shows you what he calls an address space. Another way, what he's calling address space is what I would call virtual memory. And later on, he'll switch to calling it virtual memory. So this is an example of a virtual memory address space. That's one of these guys. Now, for example, this one sits between 320 kilobytes and 384 kilobytes. That's where it sits in physical memory. But as a address space, it starts with address 0 and ends with address 16 kilobytes. That's what the CPU sees. This picture here is this picture over here. This is the virtual address space. This is a 16, he's thinking of a 16-bit computer over here. So the address space, 16 kilobytes, let's see, 16 kilobytes, that's not even 30, that's not even 16 bits. That's a 14-bit computer. No. Actually, that's kind of, I don't know where he got the number 16 kilobytes. Let's look at it. Okay. 2 to the 10th is 1 kilobyte. See, it's 1024. Okay. So you double that, 4 to the 10. I'm sorry, no, well, that's 1 kilobyte. Okay. 16 kilobytes. Okay. See, there's 16 kilobytes. Okay. Now 16 is 2 to the what? 16 is 2 to the 4. See? So that would be a 14-bit address space. Okay, so 16 kilobyte is a 14-bit. So there's 4 bits to give you the 16 and 10 bits to give you the kilobyte. So it's 16 kilobytes. So it's a 14-bit address space. There's never been, as far as I know, a 14-bit address space in any computer, but that's what he's imagining. He's imagining in his pictures a computer with a 14-bit virtual, so the program counter would be 14 bits wide. All the registers would be 14 bits wide in this picture here. Now he's not showing the CPU, but since he's thinking that the virtual memory space goes from 0 to 16 kilobytes, then he's thinking of 14-bit CPU. Okay. But on the other hand, his physical address space is bigger than that. His physical address space goes to 512 kilobytes. So his virtual address space is 14-bit. His physical address space, in thinking of this picture here, but with his example, he's got 512 kilobytes for the physical address space. So now there's a kilobyte. He wants 512. Okay, that's 512 kilobytes. Oops, I'm sorry. So notice that 512 kilobytes is actually a number 5,000 is 524,000 because the kilo is not 1,000, it's 1,024. Okay, now what's 512? 512 is, let's see, remember what power of 2 is that? 2 to the 5th? No, see, 512. I should, let's see. See, is that 9? Is that what it is? Yeah, 2 to the 9. So he's thinking of a 19-bit. Physical address space. Okay, so in his example, it's worth doing thinking about what he's doing here. This would be 19 bits of addresses to give you this, and then his virtual addresses are 14 bits. So the virtual address space is smaller than the physical address space. Okay, and that's the way things were a few years ago when we had 32-bit computers and more than 32-bit address spaces over here. So he's actually doing an example where the virtual memory address space is smaller than the physical address space. It makes it a little bit easier to give examples. Okay. Oh, I'm sorry. So the CPU, when it's in kernel mode, sees all of these. When the CPU is in kernel mode, the memory management unit doesn't do anything, and the program counter can see all of physical memory in kernel mode. Okay. When you switch the CPU to user mode, the memory management unit kicks in. The CPU thinks it's talking to all possible physical address. Actually, let me go a step back. When the CPU is in kernel mode, the CPU still thinks it's talking to all possible physical addresses. It just knows that there's a limit to how many there are. When the CPU is in kernel mode, it sees these physical addresses, and it just knows that it can't use all of its program counter. It knows that the limit is whatever. In this case here, the limit would be 2 to the 19, we said. Okay. In the case of a modern computer, this limit is going to be 2 to the 36 or 2 to the 38, depending on how many gigabytes of memory you have. So the CPU, when it's in kernel mode, sees a huge amount of memory, but knows not to, it knows there's only the first part of it, the first, say, whatever the physical address space is, it knows that it knows to only use this many bits. So the CPU, when it's in kernel mode, knows that it better only use this many bits of the program counter. When the CPU is in user mode, the CPU thinks it can use any of the addresses. Okay. And the memory management unit takes care of translating certain ones of these addresses to physical addresses and certain ones don't. Okay. So the abstraction we want is that the CPU in user mode thinks it has all possible memory addresses available to it. When the CPU, so it sees it sees the addresses from 0 up to the largest. Okay. And this is a good example of it. That process, here's another way to think about it. When the CPU switches from user mode to kernel, from kernel mode to user mode, it doesn't issue address 328 kilobyte to get to there. It issues address 0. I think that's the crux of the matter, is that when this CPU is in user mode and it wants to talk to that address, it doesn't put that address in the program counter, it puts 0 in the program counter. It'll put 0 in the program counter because it sees that memory space and it says, oh, the program code is up here at the top. It puts 0 in the program counter. Now 0 will go into the program counter, and the memory management is responsible for taking that 0 and turning it into that number. When there's a context switch and you switch from process A to process B, when the CPU is running process B in user mode, and it wants to talk to that address there, it wants to execute the first instruction in that process, it again uses address 0. Okay, notice it'll use address 0 to execute the first instruction in process A, and it'll use address 0 to execute the first instruction in process B. But we'll see it's going to be the memory management unit that translates address 0 to this address for process B, and processes virtual address 0 to this for process B, and translates virtual address 0 to this address for process A. When you switch from process B to process A, the memory management unit is going to get updated somehow. That's what the chapter on mechanism says. There'll be a change in the memory management unit. When you switch from process A to process B, something will change in the memory management unit. Address 0 will switch from being translated to that address to switch to being translated to that address. In user mode, the CPU thinks everything starts at 0 and goes up to 2 to the n, where n is the width of this program counter. In this picture, the CPU is a 14-bit program counter, okay, because this we said was a 14-bit address space, but the actual physical memory is going to be 19 bits. Okay, so the address space is bigger than the program space. The physical address space is bigger than the virtual memory space. Okay, and it's going to be the memory management unit's job to make this translation so that 0 goes, like in this case, for process C, address 0 goes to that physical address. Okay, now the reason we want that is back even from this picture from earlier in the course. When you're running this process, that process should not be able to update these memory locations. If this process could see these memory locations, it could destroy that process. It could make it do anything it wants. It could rewrite that process. Similarly, this process shouldn't see those memory locations. If this process could see those memory locations, an arbitrary user process would be able to change the operating system. It's essential for our point of view that this is an abstract computer. We want to protect processes from each other. If this process is running, it can't touch other processes. If this process crashes, it can't do harm to other processes. This process can't steal information from other processes. Okay? So the whole point of the modern operating system is this process can't mess up these other processes. So when the CPU is in user mode running this process, it can't be able to see these memory locations and these memory locations. The way in this picture, if you're running process A, somehow the CPU has got to be stuck in there. But instead of thinking the CPU is stuck between that address and that address, we don't want to think that way. We want to think that the CPU in user mode is always between address 0 and address 16,000. That's our virtual address space, our virtual memory address space, our virtual memory address space that I'm drawing over here. We want the CPU always to think it's accessing the same range of addresses from 0 to some maximum, no matter what process it's running. If you want to, over in this picture, he could have put over here that this is virtual address 0 up to virtual address 16,000. And this is virtual address 0 up to virtual address 16,000. And this is virtual address 0 up to virtual address 16,000. Every one of these processes thinks it starts at address 0. This is physical address 0. And it's where the operating system actually sits. This is not operating system code here. Okay, these are the virtual addresses. At this 0, this is the code of a process. It's not this operating system code sitting at physical address 0. I think that's why I think he should have put that this is sharing physical memory. These are physical memory addresses. This is virtual memory. These are virtual addresses. They're not real addresses. They're virtual addresses. Somebody's got to translate them from that virtual address, in this case, to whatever process you're running. 0 goes to here, or it goes to here, or it goes to here, depending on which one of these 3 processes you're running. Okay, so he's trying to describe it with these 2 pictures. Okay, physical address space holding, in this case, 3 processes, where each process looks like this, with a virtual address space from 0 to 16,000. And then he points out that within that virtual address space, it's real common to put the code at address 0. Then you have the heap, and then you have the stack. The heap grows this way, the stack grows that way. Windows doesn't do it this way, and actually Linux doesn't even do it this way anymore. This is kind of this is the way most people think of it, and it was the way Linux worked like 20 years ago. It's more complicated. Everything is more complicated now than it used to be. But this is a pretty good way of thinking about what the virtual address space of a process looks like. Okay, the program code is at address 0. The heap is after the program code. The stack is down here. The stack grows this way. The heap grows this way. You do it this way so that some programs need a lot of heap but very little stack. So then the heap can grow. Okay, some programs need a lot of stack but not much heap. So then the stack can grow. If a program needs both a lot of stack and a lot of heap, these things will meet in the middle and something crashes. If the stack and the heap hit each other, the program will usually crash at that point. It'll get out of memory error. Okay, but modern computers actually can grow. We'll see that this is the old-fashioned way of doing things. Right now, what happens if the heap and the stack hit each other, this whole picture just grows from, say, 16 kilobytes, it doubles to, say, 32 kilobytes. But that's that makes things way more complicated. So he's using a simplified picture. Okay, so this is not what's inside of here these days. Okay, in fact, we're going to see that everything is going to be much more complicated than this. This is a starting point. Okay, this is a starting point. It gives us something to think about, and we just keep making things more and more complicated as we go along until we get to till we hit what essentially is the modern operating system way of doing virtual memory. Okay, so this is the abstraction that he wants to create. It's these 2 pictures. Okay, physical memory holds a bunch of processes. Each process has got a range of physical memory allocated to it. The CPU in kernel mode knows that. It knows where process C is, it knows where process B is, it knows where process A is, it knows where the operating system is. When the CPU switches to user mode, the CPU becomes essentially real dumb. It only sees one thing. The CPU only sees a range of addresses from 0 up to 2 to the n. In this picture, I do it in a general way. The CPU sees addresses that are n bits wide. In his example, the n was 14 bits and m was 19 bits. Okay, the CPU sees this virtual address space. Virtual address 0 is where addresses begin. It doesn't. Address 0 is not this one over here. Okay, that's physical address 0. Virtual address 0 can be almost anywhere in this range here. Virtual address 0 might be physical address 0, but probably not, because that's probably where the operating system is. Actually, Windows puts the operating system at the high end of memory, not at the low end of memory. So that's another thing about these pictures. Windows, and I think I can't remember if Linux, I think Linux also, the operating system is really not at the low end, it's at the high end. Okay. In fact, on Windows, this physical address space is cut in half, and the top half belongs to the operating system. Not that it needs anywhere near that much memory, but it just was more efficient to design it that way. In Windows, the physical memory space is cut in half. The user space is the lower half, and the kernel space is in the upper half. Okay, and it's just, everything's a little bit different than what these pictures imply. The real world, everything is a little bit different than what these pictures imply. Okay, so here, but this is a good way to start thinking about it. I mean, this is actually, and this is the way things were in the 1960s. Yeah, so this picture is probably more relevant to how things were in the 60s, maybe even the 50s. By the 70s, things started becoming already more complicated than this. But this is a good place to start, to get used to the idea that we want to separate what physical memory looks like. But when the CPU is in kernel mode, the CPU can see physical memory. It's allowed to see that picture there, the complicated picture of all these different processes in memory. But the kernel modes be able to can access everything. The whole point is the kernel wrote those addresses there. The kernel mode loaded that process in there. The kernel mode loaded that process B there. It obviously has to be able to read and write all these memory locations. But as soon as you switch to user mode and you're running process A, the CPU better not be able to see any of this stuff here or any of this other stuff here. And the easiest way to do that, the most logical way to do that, was to make the CPU think when it's in user mode that it's actually running addresses between 0 and 16,000. The CPU just thinks it has these addresses. Then this thing will translate that range of addresses to wherever they belong in the physical memory space. That keeps process A from seeing process B or C. Okay, that's good. Okay. Now here's another thing that he shows all these processes as being the same size. So if you want to run a process D, you could run it right there. But the truth is that these processes don't have to be the same size. Process A might need more memory than process B. Now, suppose I wanted to run a process that was bigger than this empty space. What if I wanted to run a process that's the size of that empty space plus that empty space? Well, in this model, you couldn't really do that very well. But we'll see that what we would like to do is take process A and bump it down to here and make a big empty space in here and load a big process inside here. And that's what in the real world, that's what computers do. They'll move processes around to make room for bigger processes. This is referred to as fragmentation. Right now, this computer has 1, 2, 3 chunks of free memory that each one of these chunks is 16 kilobytes. So that's 64 kilobytes of free memory, but it's in chunks. A 16 kilobyte chunk here, a 16 kilobyte chunk here, and a 32 kilobyte chunk here. If somebody wants 3 chunks of memory, they can't get it because there's no 3 contiguous chunks of memory. We say that the free memory is fragmented. The free memory is here and here in one chunk, then it's broken up as another chunk here and another chunk here. If I want to run a process that needs 3 chunks of memory just for itself, I have to defragmentate memory. I would do that here by moving process A up a block. If I move process A up a block, then I'd have 3 contiguous free blocks. Okay. Moving a process in memory can be real complicated. In this picture, if I just thought of this process as being restricted to this range, and this process being restricted to this range, and the memory management unit just filtered out the ranges, that would work fine, except if I needed to move this process. If I needed to move this process, if it was think of an instruction here that jumped from here to here. When the process jumped from here to here, it needed to know the memory address of here. But if you take this memory and move it, the addresses change. So jump addresses might need to be modified. When you move processes around in memory, in the old days, they would have to modify the code of the process in memory as they moved it. This was called relocating. Yeah. If you move the process, and you would move it to make a bigger free chunk of memory. So you would move a process to defragmentate memory, to create a larger chunk of free memory. When you move a process in memory, in the old days, as you moved it, as you copied it from here to here, you'd have to modify it because it needed to know where it was. If a variable was at a certain address, then that variable would be at a different address when you moved it. So if you knew the address of the variable, when you moved the program, the address of the variable would move. So that was really a pain. This system here makes that work better. Your program thinks everything's in virtual memory. If your data is at address 0, your data is always at address 0. If I move this program from here to here, the program doesn't have to be modified because all the code here thinks it's based at 0. And all the code, when it jumps around, is jumping within this range. When it accesses the stack, it knows where the stack is. The stack is in this range. This is independent of where it is in this picture. If process A is here between 3200 and 3800, that doesn't affect this picture here. It's still from 0 to 16. If you move process A so that it's based at 256, that doesn't change here. So when you relocate, all you have to do is take this memory, copy it to there. So this virtual memory idea makes relocating programs easier, as opposed to this idea of this thing just being a filter, that this program's in this range of memories. This thing filters out addresses that are outside that range. But that still leaves the problem that a memory location, and a variable is at that memory location. If you move this program to another place, that variable has to have its address updated too. Okay, because the program thinks it's between this address and this address. The memory manager just restricts the CPU from addresses below that or above that. That was the way things were done for a while, but that doesn't work well because relocating programs, you do that all the time. Why would you relocate programs? Suppose you're running 1, 2, 3, 4, 5, 6. So he could run 7 programs that are the same size. So maybe there's 7 of them running, and then 3 of them quit. But maybe the 3 that quit, well, 4 of them quit. This one quit, this one quit, this one quit, this one quit. So he's got some free memory there, free memory there, free memory there, and free memory there. And these continue on running. Now process X shows up, and process X wants 3 chunks of these memory. But there's no 3 chunks that are next to each other. So you have to move one of the processes to create a bigger chunk of memory, a bigger chunk of free memory. Memory gets fragmented because processes come and go. And when they leave a hole in memory. When process C terminates, it'll leave a hole here, which makes a bigger chunk empty space here, but that empty space is 2 chunks of memory. Okay, this one would still block a process from having 3 chunks of memory. So if process C terminated, there'd be 2 free chunks of memory here, a free chunk here, and 2 free chunks here. There'd be 1, 2, 3, 4, 5 free chunks of memory, but no 3 chunk space that you could use because memory would be fragmented. If a program came along that needed 3 chunks of memory, you've got to move somebody. You've got to move process A down away or you can move process A up to create three chunks contiguous. Okay, so defragmentating memory is an important part of what the virtual memory system wants to do. It wants to make it easy to move processes around. Okay, this idea makes it easy. It's represented by this picture here. This virtual memory space doesn't really matter where in the physical memory space it's placed. All the addresses are fixed between 0 and 2 to the n. If you did move this virtual memory space, from one place to another in physical memory, it doesn't affect the virtual addresses. That's important. Okay, so this virtual memory system protects processes. That's step 1. It makes this process immune from this process because this process, when it's running, only sees those memory addresses. It doesn't see any negative addresses. It would need a negative address to enter him. Process B would need a negative address to go up here. Process B would need an address much larger than 16 kilobytes to reach down into process A. But process B only sees addresses between 0, which is this one, and 16,000, which is that one. So process B only sees that. So processes are protected from each other. But then the other thing a virtual memory does is it makes it easier for us to move processes around. Because processes are self-contained in a virtual address space where addresses are fixed between 0 and, in this case, 16 kilobytes, if I choose to move process A and bump him down to here to create a bigger empty block, I halt process A, I switch into kernel mode, the kernel copies everything in process A down to here, and then the kernel mode updates process A's memory management unit somehow. That's the step we haven't talked about. But when the kernel moves process A from here to here, what it'll just copy from here to here, and then it'll do a little update in the memory management unit. And then the memory management unit will say, oh, now process A's 0 goes to that address instead of that address. So process A can be moved. In fact, I can move at some point I could move process C up, I can move process B up, and I can move process A up, and I could have room for a really large program because I could have 1, 2, 3, 4 chunks of, I could put all the free memory together in one big chunk by moving processes A, B, and C. Okay. So this virtual memory system, it's meant to solve a bunch of problems. One is protection, okay? One is protection. You don't want process A to be able to see process B in any way. And then the other way is efficiency. We want to be able to move processes around to free up memory so that a large process can come in. Because as processes come and go, memory will get fragmented. There's no way to avoid that. As processes come and go, when process B terminates, well, he'll leave a hole, okay? He'll leave a hole that, it's next to another hole. Maybe when a new process comes in, that hole is big enough for it, but maybe that hole is not big enough and you want to move process A to make a bigger hole, okay? So he talks about in here the goals of the virtual memory system, okay? Now here he said third. Well, I mentioned that as the first goal. The first goal is protection, okay? Protecting each process from each other and protecting the operating system from the processes. That to me is the first goal. That's actually what this is all about. Efficiency is what, and there's another thing, this idea that it should be relatively efficient to move a process around so that we can free up chunks of memory. We want there to be an efficiency to this. There's other efficiencies that you want too. We want the memory management unit to be simple. Okay, so his efficiency is actually several things. We want to be able to move processes around efficiently. We want the memory management unit to be simple as possible. Okay, so we want efficiency in this. So this virtual memory space gives us an efficiency. Okay, and then there's another goal here he mentions of transparency. Okay, here's what that means. This has got to do with the way the compiler thinks. If we go back to these here, the compiler builds this when it compiles your program. When the compiler compiles your program, the compiler decides that put all of your code in a range of addresses starting at 0. The compiler decides that the heap will be, these addresses, the stack will be here, and the stack will grow this way. Then the compiler keeps track of where all your variables are on the stack. The compiler compiles your program for this virtual memory address space. The compiler does not want to know anything about physical memory. First of all, it doesn't know where your program is going to be loaded in physical memory. The compiler doesn't want to have to worry about this stuff. So the compiler compiles for the virtual address space. That makes the compiler more efficient. Okay, that makes the compiler, that makes the system transparent. He refers to as transparency. That makes this thing, it's also kind of an efficiency. It makes the compiler more efficient. The compiler doesn't need to worry about what will happen when these things get put in physical memory. It also makes things transparent. The compiler doesn't even know about the physical address space. This is essentially transparent to the compiler. There's a couple of different words you can use, but the key is that it makes things better for the compiler. The compiler thinks like this. Just like this, the compiler is programming the virtual CPU, the user mode CPU. The compiler is compiling for the virtual CPU, the user mode CPU. So the compiler is assuming that the program counter can access anything from address 0 up to 2 to the n. The compiler assumes it can put the code anywhere it wants. If it wants to put the code down here, it can. So some people think of the code, if you actually look in some textbooks, they'll show the code as being at the bottom down here. And then the heap is at the top growing down, and the stack is next to the code growing up. Okay, so some people think of the program code as at 0. Some people think of the program code as at top. Every compiler can do whatever it feels like. The compiler compiles to the virtual address space. That makes the compiler more efficient. That makes the problem of physical memory transparent. Okay, the compiler doesn't need to even consider what's going on in physical memory. Okay, all right. So these are the goals are this transparency, efficiency, and protection. Yeah, a system that makes this stuff work well. We want a system that works in, that accomplishes these goals in a transparent. Protection is actually the one thing that's hard in here. You've got to make it so that protection is the absolute core idea. Process A can't see process B. Process B can't see process A. So that's the one hard goal. The other goals are a little bit fuzzy. Make it simple, make it transparent, make it easy for the compiler. Okay, those are kind of more like secondary goals, but they actually are important. Compiler writers would have a hard time dealing with trying to write code that ran in this model here, where your program could run anywhere in any particular chunk of physical memory. If the compiler had to worry about that, that would just be a real problem. Again, if the operating system wanted to move process A, we really want a system that makes moving process A as simple as possible. Okay. Of course, the operating system can move process A in this other model. If we're using the model where this is really just a range of addresses, this process is a range from here to here. This thing filters out memory addresses. If you're outside that range, your program crashes. But essentially, you're working with physical addresses that just have to be within that range. Then if you move this process, you may have to update the addresses within here, because a variable at this address will now be at a different address. People did it in the 60s. They wrote it so that when you moved a chunk of code, when you moved a program from here down to here, you would rewrite the code essentially as you moved it. Okay, but that just wastes CPU time. People wanted a design that was better than that. Okay, so we want our virtual memory system to solve some of these secondary problems like efficiency and transparency, but its core goal is protection. Okay, that's the absolute core goal. And in fact, there's in modern sense, we're really hitting a problem. This is the core goal. These are secondary goals. These secondary goals are now starting to conflict with the core goal. That's actually happening in the modern Pentium. I don't know if you ever heard of some of the problems that are coming up with the Pentium right now. The biggest problem is something called, oh, I forget the name of it now. Damn it, what's the, oh, Spectre. Spectre meltdown. Okay, this is an attack on the modern Intel CPU, the meltdown and Spectre attacks. They were discovered about a couple years ago. They're very, very serious. And what it boils down to is that, what it really boils down to is this goal, protection, is being compromised by these other goals, the transparency and the efficiency. There's aspects of the virtual memory system that are so complicated to get this efficiency and transparency that they've made protection break down. Okay, and it has to do with some weird things involving address speculation, and it boils down to is that protection has been compromised because too many other aspects started becoming so complicated that the protection failed. Okay, and it's really a mess. It's very, very complicated. These things are very hard to explain. See, breaks the fundamental isolation between applications. See, it breaks the protection. Okay. Again, Spectre breaks the isolation between applications. It breaks the most fundamental thing that virtual memory is supposed to do, provide the protection. And the protection breaks down because there's so many other things going on that the complexity of the other things ended up being a bug. And there's so much complexity in the transparency and the efficiency and in so many of these other aspects of the CPU that somebody discovered a weird little hole in the protection mechanism. Okay, and they figured out a way to exploit that hole, and it's a very serious problem. It goes at the core of how the Intel CPUs are designed, and it's really causing Intel a lot of trouble. Stopping these attacks is, right now, these attacks are very hard to do, and nobody knows if they actually are showing up in the real world or not. I don't think they've actually found these attacks in the real world yet, but people have proven that they could be done in the real world, but they would require tremendous skill. You would need to be like the best American hackers, the best, like the National Security Agency, or the people who are doing the best work for North Korea or Russia or China. But people are afraid because these people they have billions of dollars at their disposal. Intel's enemies are nation states like Russia, China, North Korea. They have millions and even billions of dollars to spend to attack Intel computers. Because if you can attack an Intel computer, they're running Google and everything. So the fact that there is a potential isolation breakdown is tremendously important. And the breakdown really exists. There is a breakdown in this protection. Now, the question is, can anybody exploit it or not? Does anybody have the skill, the money, the patience, and the time to exploit this hole? It's not a big hole. It's a little narrow, tiny hole, but it exists. And it's caused by too much complicated stuff. And then there ended up being a bug in the protection mechanism caused by all the other things going on. Okay? So this stuff is it's vital to what these ideas are vital to what's going on right now. The meltdown and Spectre has gotten a huge amount of publicity in the computing industry because it proves the potential for a huge problem in security. If anybody can be, if they ever discover that somebody is actually using these to attack computers, it'll be a real serious issue. As far as I know right now, no one's ever found an attack in use that uses either meltdown or Spectre. And they've been around for a couple years now. I forget what year. I think it's 3 or 4 years. They've been around. No, I think they've been around 5 or 6 years now. I think they've been around. Doesn't have the date of publication on here. I think it was like 5 or 6 years ago that they were discovered. And Intel's still working on trying to patch them. They're still not solved. These are still active. They're still there. There's the potential for attacking them is still there. Intel is slowly working on, they have to restructure the internals of their CPUs in very subtle ways to try to make these things go away. Okay, so this goal is the key goal. It is the absolute crucial goal. It should be the prime goal. But in this book, we treat them all as, like, he actually mentions it as the third goal. See, I would think of it as the very first goal. But when you're learning it, you want to learn, we want to see how do we want to make virtual memory protective, how to make it efficient, how to make it transparent. We want all these goals. Yeah. And so we're going to learn the theory of how we make all these goals work. And then we'll see how things, we'll see we'll see that it gets complicated as we go along. We're not in this class going to be talking about how Meltdown or Spectre work, but we'll mention that this goal, any one of your goals, can get compromised if everything else becomes too complicated. A little bit of a bug in one of these other features could create a hole in that feature. Okay, so trying to make transparency or trying to make it efficient might open up a hole in your protection, and that's kind of what's happened. Okay, all right. So that's what we're trying to do. When we go back and fill in the hole, the big hole left right now is what's inside that memory management unit. Okay, the big hole we haven't said anything about is what's really inside there. Okay, as we fill in that hole, you can kind of go back and think about these examples, and you should do this. I mean, this stuff is not meant to be read once. It's harder than that. So you read this chapter, and it's, I think I'd be surprised if you feel like real comfortable after you read this chapter. I don't think you should feel like, oh, I really know this stuff. Yeah, it's harder than that. You read this chapter and it starts creeping into your mind. Then we'll read the next chapter, and then you should go back and reread this chapter and say, hopefully that's starting to make a little bit more sense. Okay, this is not linear. This is very non-linear learning. You go back and forth and back and forth and back and forth. That's well accepted by the people who wrote the book and by professors and people who know this stuff, because we all know that we learned it by going back and forth and back and forth and rereading and reading. But they don't necessarily say that in the book. Like the author doesn't say at some point, okay, now that you've finished chapter 8, go back and reread chapter 6 and 7. But that's kind of what you should be thinking about. You should be thinking that after you read chapter 6, this one's chapter 13 in his book. After you read this chapter, it's kind of these ideas should start settling in. But then the next chapter, well, actually, we're skipping the next chapter because it's about Linux. This is about memory in Linux. So we'll replace that chapter with the next homework assignment. We'll talk about the Windows Memory API. So the next programming assignment replaces this chapter 14. So we're going to go from chapter 13 to chapter 15. And we're going to talk about address translation. That's what goes in the memory management unit. But we're going to do it in a real simple way. We're going to do a super simple memory management unit. Okay. And then that'll help us get a sense of what's going on. And then the next chapter will make that memory management just a little bit more complicated. And that still won't be what the modern computers do. So it'll be a little bit more complicated memory management unit. Then the third version of the memory management unit is the one that people use now, paging. That's the memory management unit that is in use in modern computers, a paging virtual memory management unit. So we're going to go from what's called a base and bounds memory management unit to a segmentation memory management unit to a paging memory management unit. So we're going to fill in this box here with base and bounds, then with segments, then with paging. And the third version, and it's kind of like how we got to the multi-level feedback queue. Remember, the multi-level feedback queue was because you were really blending round robin with priority queues with shortest job to completion first. The real algorithm for scheduling was a blend of multiple algorithms. Same thing is going to be true with paging. Paging, if we just jumped into paging, it would be hopelessly complicated. But if we inch our way into paging, we see how when we get to paging, we see that it's built up out of taking these earlier versions and just making them more sophisticated. So historically and literally, paging is gotten by building up from what's called base and bounds to segments to pages. So from base and bounds to segments to pages, just like we built up from shortest job first, to shortest time to completion first, to round robin, to priority queues, and then we got multi-level feedback queue. You know, the answer is a blending of simpler things. The same thing is true here. We don't just jump to the answer. It's way too complicated. So we arrive at the right answer by building up what are historically there. It's interesting that, you know, the thing that leads up to the answer here is exactly what historically they did. They built computers with what were called base and bounds registers. Then they built computers with segments. Then they built computers with page tables. And it's still, that historical process is still probably the best way to understand it. Okay, so we'll quit there. Okay. And we'll start the next chapter on base and bounds. And hopefully that's going to make some of this discussion a little bit more concrete, because we're going to fill in an idea for the memory management unit. Okay, so we'll go ahead and quit there, and we'll meet on Wednesday. We'll do chapter 15, base and bounds. Okay, so we figure, oh, stop sharing. So meet again on Wednesday. Bye-bye.